All right. I think it's recording. I hope it's recording. Otherwise, this will all be for nothing. Well, that's not true. We'll make our way through this because we need it anyways. So yesterday, we started this unit talking about linear equations, and those linear equations, when they're plotted out on a coordinate plane, they graph as a line. So we started off with the most basic of building blocks when it comes to graphing, and that was the points, which we used ordered pairs to find where they were located, and then paired that up with creating a table along with an equation. We were able to find a really unique set of points that allowed us to then draw in a very specific line. And here's something what we're going to realize today, hopefully by the end, is that every linear equation produces a unique line. So change the equation a little bit, you change the line that you're dealing with. So yesterday I mentioned at the beginning, it was very boring and dull and repetitive, because basically you were to create the table, you picked some values for your X, dropped them in the equation, crunch the numbers, get the Y, graph. Start over, plug a new value in, same crunching of numbers, same process over and over and over and over again. Kind of dull. Thankfully today, we're going to talk about some very unique components of the lines themselves and how they relate to the equations, so we can identify those parts. And by the end of today, we should hopefully have a much more efficient process of getting to that graph that we're looking for. And then tomorrow, we'll kind of begin the process of looking at it in reverse, because by the end of the day, we're going to see that linear equations are very powerful tools. They allow us to communicate a very specific line to somebody without visually being present. If all I have to do is send you an equation and you know what that line is going to be, that's golden. That minimizes the communication, but doesn't lose the amount of information. So tomorrow we'll practice writing these equations that seem so important. So first component we're going to learn about today involving lines is its slope. So the thing about slope, my opinion, I guess it hasn't technically been proven by people more superior than me, I believe it to be one of the most important parts of a line, especially when you're dealing with graphing. So the slope of the line determines a variety of things. First off, it describes the direction in which that line is traveling. Is it going up? Is it going down? More to the left, more to the right? And kind of along those lines, it also describes its steepness. So if you think about the word slope, you walk outside on one of these hills out here outside the building, you would define them as having a slope. And the more steep that slope, the harder it is to climb, because your vertical distance is changing much more quickly as you try to move forward. So anytime you think of steepness involving lines, you're describing the slope. Now, for our purposes, oh, screen went black. Let's see here. Very glitchy today. You know what it is? It's because I'm recording and it hates me. Okay. Marissa, you can see me. Can you see my notes? It's a little laggy, not glitchy. Yes. Jay, can you see my, Jay, you cannot see my screen. Okay. Any changes there? So Miranda asked if you're on a phone, Jay. She's helping me troubleshoot because the mobile app for Zoom is a bit quirky. Miranda has a certification in tech advisory. That's awesome. You can come do my job in the afternoon. I teach IT fundamentals. You can come be a visitor for me one day.
Can you pull your screen down just a little bit?
Oh, Like this?
Yeah.
Okay. Yep. Jay, how's it going on your end? Any image yet? Okay. I think he's going to try to rejoin us here. Hopefully when he gets back in, he'll have the connection. If not, hopefully the recording is working. He can go back in and watch some of this recording as well. All right. So slope is, like I said, probably one of the most important things when you're describing linear equations, when you're dealing with graphing lines. And because of its importance, there's actually a variety of ways that you can either find it or identify it, depending on the information that you're given. So what I have for us here is 3 different scenarios, each of which we're going to try to find the slope. All that's different from one to the next is how the information is presented to us. So, for example, for the assignment today, when it asks you, what is the slope? The best thing to ask yourself is one of these 3 questions. Is it a graph? Have I been given a graph? Have I just been given 2 ordered pairs? Or have I been given an equation? Once you decide which of those 3 scenarios is true, that's going to help you decide which of these 3 methods you're going to use to find the slope. Jay, I see you joined us again. Any change? Can you see the screen? If you're talking, it's registering you, but I'm not hearing anything. Okay, good. Thank goodness. Worst case scenario, hopefully the recording works as well. I was telling the others, if anyone misses anything, in theory, you should be able to go back and watch. Miranda. Oh, Miranda says she doesn't hear you either, Jay. That's okay, Jay. As long as you can hear me and as long as you can see, we're good. So technology is always exciting. All right, so the first item on our list here is if you're given a graph of a line and you are asked to find the slope, we're going to do what is called count the rise over run between 2 points on the line. So in fact, I'm going to zoom in here real quick and I'm going to highlight rise over run. I'm also going to highlight that we need 2 points on the line. So I'm going to zoom out a little bit more here again. Now, it doesn't say it has to be any specific points. I would suggest, though, because we are counting, and counting by decimals and fractions would be no fun, I would suggest we choose 2 points that are on nice, clearly red coordinates. So again, it doesn't matter. We could pick any of the points so long as they're on the line, and we should still come up with the same slope. So looking at the graph here, I'm going to pick the ordered pair -3, -5. And I'm also going to pick the ordered pair 3, -1. Now, those aren't the only points I would have to use, but they are clear-cut coordinates. And here's the reason why I'd like them to be on these clear coordinates. Those grid marks are going to be kind of like city blocks. I'm going to count how many blocks I have to go up or down, so that would be the rise, before I then run either left or right. Now, as with ordered pairs, direction is key when it comes to determining the signs. So long as you have 2 points, you pick whichever one you want to start at, and then you start counting. So let me change my pen color here. Let's go green. So I'm going to start at -3, -5. How many units do I have to rise to get at the same level as the ordered pair 3, -1? 4 units up. Now, is up described as a positive or negative direction?
Positive.
Positive. Use your axes as a clue. Up on the y-axis is a positive direction. So at any point traveling up anywhere on the coordinate plane is considered a positive direction. So going up 4 units, this is going to be my positive 4, which is going to refer to my rise. Now from there, how far am I going to have to run?
Six.
6 units to the
Right.
To-
Positive.
so 6 units. Yep, I'm on the front side where it has 3 examples across the top. So not that side, the other side. Yep. So 6 units to the right. Right is a positive direction. So I'm going to write my 6 right here. This is going to be my run. Now, according to the notes up above, rise over run is all I need to evaluate slope. So if I think of that relationship, rise over run, in our scenario here, our rise was 4, our run was 6. Now, that is technically our slope, but as with any fraction, what should we always look for an opportunity to do?
Simplify.
Simplify whenever possible, because the smaller the values, it doesn't change the fraction, it just changes how it's perceived, and it looks like it's smaller. So for example, 4 over 6 would simplify to 2/3. So 2/3 equals my slope. Chris, let me grab you a set of notes. You're welcome. All right. Oh, of course. I stepped away and I got scared. You know, I bet it is. I bet Tammy tried to connect to my Zoom meeting. Kicked me off. Okay. We'll fix this. Maybe. Miranda could still see. It kicked it off my screen though, so everyone in the room was still struggling. All right, back in business. Hopefully everyone can still see. Hopefully I haven't broken that. All right. Good. Of course, on the day we're going to record is going to be the day that literally everything happens. So your guys' patience is much appreciated. So one thing I want to talk about before we move on to the second scenario here is the fact that we counted up 4 units and to the right 6 units. And I'm claiming that we didn't have to use just those 2 points or specifically those 2 points to figure out the slope. In fact, some of you may notice that there was also the y-intercept that we technically could have used. There was also, if you looked at the very, very edge, technically there was even a 4th point there at the very edge. And I claim that it doesn't matter which of those 2 points you use, you'd still find the same slope, assuming that you took that last step of simplifying. And here's the reason why. Let's assume, I'm going to use my laser pointer here. Hopefully it transitions very nicely. If I had started here and I told you that the slope was 2 over 3, in terms of rise over run, I would go up 1, 2 units, and I would run 1, 2, 3. And would you look at that? I'm back on the line again. Repeat that process. Go up 1, 2. So that's my rise. Run 1, 2, 3. Sure enough, there I am. Do it one more time. Rise, 1, 2, run, 1, 2, 3. If I had a bigger coordinate plane, I could go up 2, right 3 again, up 2, right 3 again, because the slope is describing the direction it's traveling, the exact direction it's traveling. And because a line never veers off of its course, because by definition it is straight, it's going to repeat that pattern forever and ever and ever and ever. So even if I started at the very first point here and I counted up 1, 2, 3, 4, 5, 6 for the rise and ran 1, 2, 3, 4, 5, 6, 7, 8, 9. 6 over 9, guess what it also simplifies to?
2/3.
2/3. So good news, it doesn't matter which 2 points you use, so long as you count carefully, consider your signs carefully based off of the direction you're traveling in, and then make sure at the very end, simplify that fraction if possible. So that is how we find the slope given a graph. Second scenario is what we do when we're given 2 ordered pairs. So for this scenario, we actually introduce a formula. One of the first formulas we'll use in this unit. So this is called the slope formula. And just on a little side note here, anytime you see from this point on the letter m, a lowercase m, we use that to denote slope. So anytime you see m used in a formula in this unit, m is representing slope. But then in the rest of this formula here, we have this y2, this y1, x2, x1. Technically, this would be called y sub 2, y sub 1, because they are subscript on the values. But we haven't seen anything quite like this until I think about what it is I have been given. What are these called again?
Ordered pairs.
They're ordered pairs, and each ordered pair consists of what?
An x coordinate and a y coordinate.
An x coordinate and a y coordinate. So if you think about it, if you have 2 ordered pairs, you have 2 x coordinates, you have 2 y coordinates. Kind of makes sense then that you would label each x and each y separately so as not to get them mixed up. And here's what I strongly suggest doing before trying to plug into this formula and just go. Take a look at your ordered pairs. Your first ordered pair, label that your x, helps if I have the right tool. Label that your x1 coordinate and y1 coordinate. Second ordered pair will be your x2 coordinate and your y2 coordinate. And the reason why I suggest labeling them before you use them is so you hopefully don't accidentally mix and match them, because where they land is very specific in the relationship that they're going to have. So what I'm going to do here real quick is I'm going to write down a little template here for the slope formula. So we're going to end up replacing the y2, the y1, the x2, the x1, but something that always has to be there from the beginning are these subtraction signs. That is part of the formula. Everything else in these empty slots is going to be where we put our replacements. So just going along with that formula here, the first, I'm going to start at the top, start at the left. y2 is a -4 minus y1, which is a +2. So on top, I should have -4 minus 2. On the bottom, first one is x2, which we've put on our -5, and minus x1. But if you notice, there is a subtraction sign from the formula, but we're bringing in another negative sign to go along with it. Highly recommend anytime you're doubling up signs like that, wrap that second value in parentheses so that you don't accidentally assume that the subtraction sign and the negative sign are the same piece. They are two separate items. The subtraction sign came from the formula. The negative sign came in with the 3. Morning, Toby. Get you a copy of these notes. You're welcome. All right. So again, as I mentioned from day one, if anything's going to trip us up, it's going to be these darn signs. This is one of the situations where those signs often get crammed together too quickly, and we make little mistakes. So good news, we're looking for slope. Slope is represented by m. M is already by itself. So really, I'm just trying to clean up this right-hand side. So I'm going to have m equals, on the top, -4 minus 2. What would that give me?
-2.
Not quite. They're both negative.
-6.
It'd be a -6. So I have a question here from Jay. So yeah, so where we put the question here is that, so you put 2 and -4 on top and the -3 and the -5 on the bottom. The reason for that specifically is based off of the fact that the bottom is where the x coordinates go. The top is where the y coordinates go. Now there is a way to tie this into rise over run. If you think about it, rise is a change in your y coordinates. Run is a change in your x coordinates, which is why they land where they are in that formula. Now, what you want to be careful of though is if you start with the second y coordinate on the top, you have to start with the second x coordinate on the bottom. You wouldn't want to accidentally reverse one compared to the other, because then you're going to get the right slope with the wrong sign, which is exactly wrong, unfortunately. But for this example here, on top, -4 take away 2 is -6. On the bottom, oops, -5 minus a -3. Remember, subtracting a negative is the same as addition. So technically, this is a -5 plus 3, which is a -2. Now, this fraction also can be simplified. If I leave it as a fraction, first off, double negative becomes a positive, and 6 over 2 simplifies to
3.
If I divide it, yes, I'm going to actually write it two ways. If you left it in a fraction form, you would write it as 3 over 1. Or you could write it as m equals just 3, like you said, Jordan. Now, both are correct. What we'll see towards the end of our notes today is that if I were to try to graph from this information, I really prefer my slope to be like a fraction. So anytime that it's not, we'll do a little trick where we write a 1 underneath, because that's going to give us that rise and that run to trek our way across the coordinate plane.
I have a question.
Yeah.
Are we always going to try to get it down to like the last number, like simplifying the fractions or whatever?
So sometimes, so this one was kind of a special one, that it technically simplifies all the way down to just a nice clean number.
Mm-hmm.
They won't always do that. In fact, most slopes, I would say, would typically simplify down to a fraction like we got on the earlier one.
Okay.
I would say that that's probably more common out of the two scenarios.
And when you have like your numbers in the parentheses for your x and y, is your y always going to be on the right and your x always on the left? Like for that m equals.
In terms of the ordered pair?
Yeah.
Yeah. So if you think about it, an ordered pair always will have an x and a y coordinate. And if you ever forget which order they come in, It's alphabetical. X always comes before Y.
Okay.
So that's a good question. Yeah, it's some of those little things that we sometimes don't think about that we take for granted until all of a sudden it's test day and we're like, which one's my X, which one's my Y? I've been doing it this whole time. Oh no. Lost connection again. I told you recording. It's just bad news. Okay, I'm gonna pause my recording. Okay. So yeah, just to summarize again what we were just talking about before it glitched out on us. In the ordered pairs, our X coordinate always comes before our Y coordinate. They're alphabetical. So far, again, to summarize, we can now visually find the slope from a graph using this idea of rise over run, or algebraically, we can find it by finding the difference between our Y coordinates over the difference in our X coordinates. Yes, Toby.
How did you figure out the rise over run?
How did I figure out the rise over run?
I mean,
That's okay. So the rise over run, we had to find 2 points on our line. The rise was how far we had to travel either up or down to get to the same level as the second point. And then the run was how far we had to travel left or right. So in our case, on this first example here, we had to rise 4 units and then run 6 units to get from one point to the next. But then we found out, well, 4 over 6 simplifies to 2 over 3, which is our final slope. And then the second one here, we just used a formula, which I was going to box in these little answers down here. Either one of these would be correct. If I was just asking for the slope, I wouldn't care. If I was asking you to graph, I would strongly recommend think of that 3 as a fraction. And any whole number or integer can be expressed as a fraction if you write it over a 1. Last one, probably the easiest, assuming that the equation is written in the format that we like. And you're going to hopefully by the end of today, or if not today, then tomorrow, become very familiar with this form called slope-intercept form. So when you're given an equation, if at all possible, we like to get our equation in what's called slope-intercept form. Oops. Now, I will always challenge you during notes or during review to try to remember it by name. But what's more important is recognizing what it tells you or what you can do with it. So some things that I'm going to pick out here before we actually utilize it. First off, we know it's in slope-intercept form because the y is by itself. The y has to be by itself in order for it to be considered in slope-intercept form. Once that's accomplished, you can identify 2 very important parts. The first one we just introduced today is our m, which represents our slope. So right off the bat, with the equation in slope-intercept form, you automatically can pick out the slope. It is the value next to the x. This last item seems kind of random. It's labeled with a b, but we actually have talked about this once before. The b is the y-intercept. So that would be in yesterday's notes. But to recap, a y-intercept is the exact point where our line crosses the y-axis. Now, I've given you an easy one to start this one off. Is this equation I've given you in slope-intercept form?
no,
So you say no, why not?
because there is no y.
There's no y. Are you sure?
Yes. There is a y. It's y equals negative 5/2 times x plus 8.
So there is a y. Why do I like where that y is at?
By itself.
It is by itself, which means that this is in fact in slope-intercept form, which is good news for me. Because from slope-intercept form, I can identify two parts. What is my slope?
Negative 5/2.
-5/2. Now you'll notice that the computer put the negative sign next to the whole fraction. That sometimes causes some confusion. A strong recommendation, only from experience, I would move that negative sign up to the top, because it's a whole lot easier to think of just one of the pieces being negative instead of trying to imagine the whole thing being negative. This will help more when we get into the graphing later. Now, I know it didn't ask for it yet, but because we already talked about it, what's the y-intercept? +8. It's just asking for slope, but from slope-intercept form, it's so easy to identify those parts. Why not shout it out?
So I have a question.
Yes, Marissa.
So I see where you have the y equals and then the 8. Is that why the y-intercept
So when you
in the first
mean,
of the problem
are
next to
you
the
talking about
y?
this y here?
Yeah.
So that y and this x nestled in there are describing a unique relationship between all the x coordinates and all the y coordinates of the points in that line. So the
Okay.
y is just y. The x
Okay.
is just x. This is where it gets a little fuzzy. The y-intercept is usually labeled with a b.
Oh, okay. I see where you're talking about the b equals 8 now. I didn't realize that like up at the top.
Gotcha. Yeah,
Okay.
so the y is just y. The b is the y-intercept. So there's some crossing of wires there. So I could understand why you needed that clarification.
Thank you.
It's fuzzy. Yeah, no problem. That's a good question. So 3 ways to find slope. Given a graph, we'll do it visually by using rise over run. Given 2 ordered pairs, we'll do it algebraically with the use of the slope formula, plugging it in, simplifying, watching our signs. And then if we're given the equation, so long as the y is by itself, meaning that it is in fact in slope-intercept form, then it's just a matter of identifying the 2 pieces, one of which, of course, is the slope. Now, if slope-intercept form is so important, it's probably worth knowing what to do if your equation isn't already given to you in slope-intercept form. So, good news is slope-intercept form is going to be our preferred form today. It tells us the 2 pieces that we're actually going to need for graphing, which are the slope and the y-intercept. So on this first example here, we're in luck. Why am I in luck? Because it's in slope-intercept form. And how can you tell me that? Because y is by itself. So even if you wanted to visually see it, y equals mx plus b is the very generic form of slope-intercept. Yeah, slope-intercept form. So it just lines up nicely. So because it's already in slope-intercept form, you should be able to tell me 2 things. First off, what is my slope?
2x.
Almost. I'm going to nitpick real quick. So you said 2x. Technically, it's just the 2. X is its own thing. They're always side by side, but the slope is just the coefficient, just that value connected to it.
So the equation will be y equals 2 times x minus 7.
Y equals 2 times x minus 7. If you wanted to think of it that way, that would That would hopefully help with the distinction. It's a good idea. What's my y-intercept? -7. Good job bringing that sign with it. So whatever that value is there at the end, the sign stays attached to it. So for this first example, already in slope-intercept form, identifying the slope and the y-intercept is just a matter of knowing where to look. No funny business, no manipulation, no changing of signs or any formulas or tricks. So long as the y is by itself, you can identify these two parts very quickly. Now, of course, as we know, very rarely do things get handed to us the way we want them, which at this point, then I introduce this example. Right off the bat, what do you notice? Y is not by itself. So overcome the temptation. And sometimes students will say, well, I know there's a 1 there next to x. And so far this whole time, the slope has been next to x. And they would tell me right now that the slope is 1. And then they either pick between the -3 and the 12, and they say, one of those is the y-intercept. No. We can only come to that conclusion if it's in slope-intercept form. This one is not in slope-intercept form because Toby said y is not by itself. So I don't know yet what slope or the y-intercept is. So I have a goal now. I need to get y by itself, which is part of that little blurb right up above. So this is where we're going to take skills from unit 1 and apply them here in unit 2. And they only take on a very slight difference. What doesn't change, though, is my recommendation for organization. So that equal sign is very key. I don't want things jumping around unexpectedly without me knowing why. Missy, you have a question? Just checking.
No.
Okay. I heard a noise and you're a little.
Oh, that was my pen. Sorry.
Okay. Just checking. All right. So our goal. We'll write it here to the side. Get y by itself. So currently it is on which side of the equation? On the left. Is it the only thing on the left side? No. So from the left side, what do you think we should move first? The x, or if you want to identify it as 1x, perfectly fine. How would you make that entire term disappear? Subtract it, because if you think about it, 1x minus 1x is 0, or 0x, which means 0 disappears. Now, this is still an equation, so any change you make on one side, you have to do the exact same change on the other. Now, don't get lazy on me here. If you are moving or subtracting 1x, don't just write -1. Write -1x. Because otherwise, you might accidentally goof up here at this step. So on the left, 1x minus 1x is gone. I bring down my -3y. But then I need to talk about what's happening here on the right. Is 12 and -1x, are those like terms? No. So sometimes I have students very tempted here to say, well, 12 minus 1x is 11x. That would only be true if that was 12x minus 1x. So because they're not like terms, I cannot combine them. And if you can't combine things, all you're left to do is write them side by side. Now, technically, you could write it one of two ways, 12 minus 1x or -1x plus 12. Technically, either would be acceptable, but because we're going for a very particular format, y equals mx plus b, I usually suggest keeping the x term as the first thing right after the equal sign. So the -1x drops down, the +12 drops down. I don't combine them, just bring them on down. Now, is the y by itself?
Yes.
Are you sure? No, what's still on the same side as the y? The -3. So if this was just a regular old equation, how would you break that -3 off of the y?
You would take 12, subtract it to 3. That's
Nope.
how I do it.
12 is on the right-hand side. 12 is good. It's not on the same side as my y.
You would take
You divide.
So Toby said focusing on the -3, and Marissa, I heard you say divide. Miranda, you're commenting the same. I would agree. Anytime you have a value next to a variable you're trying to get by itself, butted right up against it, that's going to be where you divide. Now, here's where it takes on a slightly different form from the equations we were solving in Unit 1. So I am dividing every term on the left by -3. Now, depending on who your math teacher is, they may first write it like this. I'm going to suggest against it. So you may see some people say, well, I'm going to divide the entire right-hand side by -3. But what inevitably happens is they only divide one of those two terms by -3 and not both. So what I recommend is divide each term separately by -3. Because if you think about it, every term on the left side divided by -3. Every term on the right side divided by -3. And that'll allow us to kind of section it out into smaller calculations as we go through it. Yes.
Sorry about that interruption.
No, you're fine.
So when you're obviously, I see what you're doing on the left side. You're canceling that out, so that 3y is by itself.
Right.
Now, by doing the balancing act here and putting that on the other side, when you do it that way, it becomes -1x plus 12.
Yeah. So you were out for this part. Why could I not combine these into something like 11x?
Because one has a variable attached to it.
So by definition, they're not like terms.
Okay, so but you can put a plus sign between them.
Right,
Or you put
because-
a sign between
Yeah, because I just put the sign that belongs to this 12.
them. Okay.
So the 12 is positive, which is why it stayed positive when I dropped it down. The 1 was negative because of the step we took. So it stayed negative as we dropped it down. Can't combine it, so just bring it along for the ride. So where we're at now is we're still trying to get the y by itself. So we're breaking off that -3 using division as if this was just any other equation. But where it starts to look a little bit different is when we start to clean up the right-hand side. Left side shouldn't surprise us too much. -3 divided by -3 is a +1, and we like to hide those positive ones rather quickly. The right-hand side, we need to be a bit more conscious of each of these two divisions. And the first one is usually the one that makes people a little bit weirded out, because usually what happens here is it results in a fraction, but it's a fraction we want to make sure is in fact simplified. So my question for you, does -1 divide nicely by -3? No. Put it in a calculator, it's going to spit out a decimal. Don't want a decimal. I really want to try to keep it as a fraction. So is there any way that -1 over -3 simplifies? No, in terms of the numbers themselves may not appear to change, but what about this double negative? It does become a positive. So -1 divided by -3 would become a positive 1/3. And what I like to do at this step, because it's going to help me pick out my slope and y-intercept here in just a moment, is I like to slide that x out beside that entire fraction, so that that fraction is very distinct, very prominent in this equation now. But then I move on to that last division. What's +12 divided by -3?
-4.
-4. Why am I happy now with this equation? Because it's in slope-intercept form. And why do you know it's in slope-intercept form? Because y is by itself. So I'm not done yet, but I'm going to celebrate in this. OCD kicks in. going to celebrate for just a moment because we took an equation that was just kind of scrambled together. And what we got to is a scenario where y is now by itself, which is a very unique format. So Jay's asking a question, asking what, well, clarifying that we don't use cross multiplication. So cross multiplication is when you have two fractions set equal to each other. Because all we were doing here was dividing each term individually, it's not quite like the proportions we had from unit 1, where you had one big fraction set equal to another. Here we're just doing individual divisions. This one cleaned up, leaving me with y. This one here cleaned up to give me a positive 1/3 x. And then the positive 12 divided by negative 3 gave me the negative 4. They're just little divisions. So that's a good question. Kind of looks like a proportion, but a little bit more involved. Now, is this still the equation, same equation we started with?
No.
Trick question. It is. It is still the same equation. All we did was change its appearance. So the reason why we're allowed to do this, the reason why this is useful, is that this equation we landed on is the exact same equation we started with. We just moved a piece to the right. We divided everything by negative 3, which changed the way it looks. So this is still the same line, but now it's in a format that we can actually work with. Because in this form, we can identify two very key parts. What is our slope?
1/3.
Positive 1/3. And our y-intercept?
-4.
Is a negative 4. So with a little bit of additional work, getting that equation in a format that was useful to us, we were able to identify two very important pieces of this unique line. So sometimes you're going to have everything you need. It's already going to be in the format that you want. You'll be able to jump straight to graphing, which we haven't done yet. Other times, you're going to need to manipulate that equation so that it fits your needs. And your need today is that we really need them to be in slope-intercept form. So slope-intercept form is key. Questions so far? Sometimes I'm bad about pausing. If not, we can move on to see just how useful slope-intercept form is to us in comparison to the very boring method you used yesterday for graphing. So, graphing linear equations, as I've kind of alluded to several times now, is very easy if you have your slope and your y-intercept. And the reason for that, and I try to kind of pick it out in this little prompt here, is because the y-intercept is a very distinct point. It is the exact point where your line crosses the y-axis. We're going to treat it as if it's a starting point. Now, I threw starting point in quotations because technically a line doesn't have a starting point because it goes on forever. But for our purposes of graphing, it is our first point we'll get on the coordinate plane. With that there, with our kind of our starting point, we can then use the slope to determine which direction it's going. Is it going up? Is it going down? You know, up to the left, up to the right, down to the left, down to the right. Where's it going? And how quickly it's going there. So how steep it is. So the recommendation I threw in here as well is that it is best to think of slope, dang it, as rise over run in this situation. So if your slope is not already a fraction, write it as a fraction. So the best way to see this is just to jump into it. So I'm gonna bring this one up here real quick, give my Zoom students a moment to jot this down. But why am I already excited? You're saying it's already in slope-intercept form. How do you know? Y is already by itself. So let me ask you this. If it is in fact in slope-intercept form, what can you tell me about this line?
You have the rise over run of -4/1.
A rise over run, or in other words, its slope. So we'll jot this down here. And I think I heard you said -4/1.
Yeah, anytime it's like a -4, it's automatically just a 1. It's not like a -1.
Right, because here's the reason why you wouldn't want to accidentally write -4/-1. What would a double negative turn into?
A positive.
And you don't want to change that slope that is clearly negative
Okay.
accidentally into a positive. So if there's only one negative sign to begin with, don't put an extra one in there. So our slope is -4/1. So good job already converting that into a fraction. If it's already a whole number or an integer like this one is, writing it over 1 gives us that visual rise over run that we'll need. What else can you tell me about this line?
There's a y-intercept of 2.
A y-intercept of +2. So simply following the instructions up above, which of those two pieces of information can I start with right now?
Y-intercept.
The y-intercept. And clarify for me again, what is a y-intercept?
It's where the point where you cross the y-axis.
So it's very literally a point, and our point for this one is located where on the y-axis? Up to.
From the origin.
Yep, from the origin. So on the y-axis, find +2, and this is our y-intercept. So here's what I'm going to do because it's notes. I'm going to label it for this first one, just so we can refer back to it later if we need to. So I'm going to point this out like such. So we remember why we were able to just throw a point in there, what felt like willy-nilly. Now, so we kind of have a location. We kind of have an idea about where our line is, at least for one point. But in order to graph a line successfully, you need, we mentioned yesterday, at least 3 points or more. Today, we can do more very quickly. Now, we use the y-intercept. What does that leave us with to use as well? Or what have we not used, I should have said.
What can't we use?
Yeah, so we've used the y-intercept. Do we have any other information? Oh, Miranda on our chat here says slope, and Jay's saying that slope of -4/1. So it may actually help, although we didn't explicitly say it, to actually, scratch that. Jordan, you did say that. You described it earlier as rise over run, and that is exactly how we want to imagine it. And the only point we have to start from is that y-intercept. So I'm going to change my pen color here real quick for this first visualization. So according to a slope of -4/1 from the y-intercept, where am I going to travel according to the slope?
Down 4.
Down 4 units. So that takes care of the -4. And then
Right 1 unit.
I'm going to travel right 1 unit. So there's my rise.
I can't hear anything that you're saying.
Uh-oh. Let me see here.
It might be from her end because I can hear you.
Okay.
It was messing up on me yesterday and I had to click out and then hit the audio thing.
Okay, so Miranda hears me, Marissa hears me. So, okay, so let me throw her a message here. Okay, so it looks like her audio, there we go. Maybe it's Alexis, how about now? Can you hear me, Alexis?
I'm gonna leave the class and then join again because I can't hear you at all.
All right. Okay. Today, if everything's going to break today, at least we'll get it out of the way this morning. So, all right. So the down 4 took care of our rise from our slope. The right 1 took care of our run, which lands us here at the ordered pair 1, -2. Now, when you're graphing today on the assignment, I don't need you to write out that visual representation every time. Because these are notes and this is something that you're going to reference back to later, I do it once. But if I was doing it by hand myself, I would have just started here and counted 1, 2, 3, 4 down, right 1, and then I just put a point. I wouldn't have all this extra stuff in here myself. In fact, I'm actually going to do it one more time. 2 more times technically. I'm going to go down 1, 2, 3, 4, right 1, and that's going to give me a third point. Now, one trick I didn't show you explicitly yet, but some of you may be guessing at it. Technically, I could do this backwards so long as I did the exact opposite. Because if I were to retrace my steps, but still think of it as rise over run, I could go up 1, 2, 3, 4, which would technically be positive, but I would get the negative by going left 1. Up 1, 2, 3, 4, left 1. Up 1, 2, 3, 4, left 1. And very, very quickly, with what I would argue is minimal work, no several sets of calculations, I found 4 points relatively quickly. And then I just need to grab some sort of straight edge or a ruler if you have one handy, draw my line, and it's done. So notice in terms of the extra work kind of sitting around my coordinate plane here, very, very, very minimal. In fact, I wrote even more than I would expect from you on an assignment. If it's already in slope-intercept form, graph your y-intercept, count out your rise over run, find a couple more points, draw your line, boom, done. The hardest part is identifying those pieces so that you're using the right values, you're using the appropriate signs. Pretty quick. Questions on that one? Slightly easier case. We're going to look at a secondary example here. But again, arguably still pretty minimal in the amount of work needed to complete. But if you're looking ahead at the second one, why am I going to grumble a little bit? It's not in slope-intercept form. And how do you know? Because y isn't by itself. So we have some work to do up front. So this one will require a little bit more work, but thankfully, once we do it the first time, it's set for the rest of our problem. So I'm going to come over here. If you're following along on the physical copy of notes, I'm going to kind of write mine down off to the side here. Oh my goodness. Make my screen freak out. All right. Off to the side here because I need a little bit of work to do this manipulation. So I'm going to copy down this equation, 2x minus 3y is equal to -12. I'm going to throw in my little guideline here, and then I'm going to get to work. Which side is my y on? It's on the left. That's where we're focused. What would you move first off of the left-hand side?
2.
Not just the 2. Let's bring the whole 2x. Let's get it out of the way. How would you make it disappear on the left? Subtract it. Because 2x minus 2x is gone. But remember, whatever you do on one side, you have to do the exact same to the opposite side. That takes care of it on the left. Drop down our negative 3y that's still sitting there. And this is going to equal, am I going to combine those? No, not like terms. So I'm just going to write them side by side, negative 2x followed by negative 12. Then what? I don't want the y to move. So you're close.
Everything by negative 3.
Divide everything by the negative 3. The y is good where it's at. It's the negative 3 I need to break away from it. And I'm using division, so I want to make sure that everything gets divided by that negative 3. So on the left, negative 3 divided by negative 3 is positive 1, which I hide, leave me with y by itself. On the right, there's two separate divisions here. Don't try to do them all at once. Just be careful. Does negative 2 divided by negative 3 simplify?
Yes.
In what way?
Positive 6.
We're dividing, not multiplying.
Oh, positive 3. It would be a
Getting-
simple. Wait, never mind.
So 2 over 3 won't simplify, but the double negative will turn positive. Miranda's right just as soon as I said it, she threw it in there. So the negative 2 over negative 3 will become a positive 2 over 3. Leave the x nearby, kind of helps us mark the spot because we know the slope usually sits next to it. And then what about negative 12 divided by negative 3?
Positive 4.
Positive 4. And with just a little bit of work, we're kind of in the same scenario now that we were with the one previously. Y is by itself, which means I can identify what two pieces?
Your slope, which is 2/3, and then your y-intercept, which is 4.
Our slope is 2/3. And our y-intercept, which is positive 4. So once you've found that information, you're ready to graph. The one that you start with is the y-intercept. The y-intercept is describing a point. We can find points relatively quickly. So this one happens to be on the y-axis at positive 4. So we'll put our point there. But from there, according to our slope, where are we going to travel? Up 2, and then you said right 3. 1, 2, 3. Now I hit the edge of my graph pretty quickly this time, and ideally I'd like at least 3, if not more. What could I do in reverse to get some additional points?
Even -2, -3.
Right. So we originally had it as a double negative, which we know is still positive. So down to left 3, down to left 3, down to left 3 should give us 2 more points before we hit another edge of our graph. So Miranda's got that as well. Down to left 3.
So we're reversing our slope. If one of the numbers is negative, we just move the negative sign. But if both of them are positive, then we just make them both
Negative. Yes, that's a good way of thinking of it.
I was trying to figure out, is there some method to that madness?
Or if you want to think of it this way, you just make both parts opposite signs.
Okay.
If that helps
That's
as
what
well.
that's doing, yeah.
Yeah.
Okay.
So however it makes sense in your mind, that's exactly what you're doing.
Okay.
But yeah, now that we've got 4 points relatively quickly, 2 negatives makes a positive. Yep, Miranda's absolutely right. That's why it still equals out to the same positive slope that we're looking for. I grab my straight edge, draw in my line, and I'm good to go. Not bad. So even though on that second one, we had to do a couple steps to get the y by itself, would you agree that that's still less work than making a table? Yeah, especially if you, I mean, even if you're doing the bare minimum, you had to do 3 sets of work to get 3 separate ordered pairs. And the other problem that some of you may came across yesterday in trying the assignment, some of those values that you chose, did he give you points that ran off the edge of your graph?
I got slammed at work last night.
That's okay.
Lunch break, so I didn't do my work.
So Miranda's saying, yeah, it happened to her. I know Jay and I worked on a problem yesterday. He chose a couple X values that, without knowing what was going to happen, ran us off the edge of the graph. And that's one of the drawbacks of the table. You're not sure yet where that line is going to land. With this part, though, you find a really clear point and then you just expand out from there. Saves you a lot of extra time and hassle. Now, icing on the cake. What happens if you remove the equal sign and in its place put an inequality sign?
Same problem.
It's essentially the same concept, but now the relationship is still linear and there's still a line involved. But if you think about this from unit 1, when we solved an equation, we got exactly one solution. But when we solved an inequality, we found a shaded range of solutions. There was shading involved. The same is going to apply here. So if you notice, the first 2 steps are the same. Graph the y-intercept, use the slope to find more points on the line. Where it changes, before you go to grab that straight edge and draw in the line, you're going to have to consider which inequality sign you have. So the inequality sign is going to tell you 2 things. First off, it's going to tell you the type of line that you're using. If it is greater than or equal to or less than or equal to, it'll be a solid line. If you want to tie it back to the last unit, think of that. That's the same reason that we had closed circles. Closed circles now on a coordinate plane equals a solid line. Less than or greater than symbols, so no equal to part, is a dashed line. On the number line, that's where we've made open circles. So there's a connection there. Lastly, because there was always a shaded area, it also is going to tell us where to shade. Now it's a little bit more involved because we're not going to shade just to the left, just to the right, because now we kind of have an extra dimension in there. We also have up and down now. So once you get your line in there, solid or dashed, depending on the sign, you're then going to choose whether to shade above it or below it. So let me show you what that looks like. Well, unfortunately, what's already an issue?
Got to turn it into slope-intercept form.
I need it in slope-intercept form. So even though it's not an equation, it's an inequality, the goal is still the same. I want the y by itself. So let's.
So y greater than or equal to m times x plus b is still slope-intercept form?
Yes.
Okay.
So, and that's why I tried to be very generic in saying that the y has to be by itself. I didn't really say anything necessarily about the sign itself. Y needs to be by itself. And right now it is not. And if it helps, let's put that 1 next to the x, since that's probably going to be the first thing we move, right? How would you move that 1x? So subtract 1x from both sides. So far still feels like an equation. So it leaves me with negative 2y on the left is less than, are those like terms on the right?
Nope.
They are not, so just bring them both down. Negative 1x, positive 10. Then what would you move?
You would divide -2 by all numbers.
From everything?
Yeah.
So everything is going to get divided by a -2.
Might be getting ahead of the game here, but since we're dividing by a negatives or sign flipping.
You're not getting ahead of the game. So something I assume was buzzing in the back of your brain. We said inequalities. We just said divide by a negative value. Last unit, anytime that happened, the sign flipped on us. Those rules didn't change. Just because the equation's a bit more, well, inequality is a bit more involved, that rule still applies. Anytime you multiply or divide both sides by a negative value, your sign will change directions. So that less than symbol is now a greater than symbol. Y is thankfully by itself, but just like the equations, we're going to clean up that other side. So -1 over -2 should be
Positive 1 over 2.
Yep. Positive 1 over 2. X is still hanging out there. 10 divided by -2 is a -5. So if you want to, I didn't write it down, but you're more than welcome to. Maybe off to the side here somewhere. Remind yourself that anytime you divide both sides of an inequality by a negative value, that sign changes directions. Now, here's what I'm going to do. I'm going to list all the information we can now pull from this in the order that we're actually going to use it, following the 1, 2, 3, 4 from up above. For step 1, we will need the y-intercept. What is my y-intercept? A -5. Second thing it says we'll use is the slope. What is my slope? 1 over 2. Third thing it says is we'll need to know what type of line. And for that, we look at the sign. Greater than symbol tells me dashed line. And the last thing I need is to know where to shade. Again, the inequality sign tells me that as well. So greater than symbol tells me it's a dashed line, but it also tells me to shade above. So those are the 4 pieces of information I need to successfully graph this linear inequality. So I'm going to slide over here and start putting it on that graph. We know what to do with the y-intercept. We're going to find that -5 on our y-axis. We're going to put a point. Then the slope is going to tell me to go where?
Up 1, right 2.
Okay, up 1, right 2. And it looks like I can do that a couple times. And if I wanted to squeeze in 1 extra point, I could also go down 1, left 2. So again, so far it feels like we're doing just a regular linear equation, but here's where it changes. What type of line are we graphing?
A dashed line.
A dashed line. Now, if you accidentally draw a solid line and realize it after the fact, don't erase the whole thing, just erase some notches out of it. I'm not going to be that picky. And then last but not least, where, with respect to this line we have now put on there, where are we going to shade? Above it. Now, some people think, oh, that means above the x-axis. No, no. Once you get your line on there, I don't care about the axes anymore. I am talking with respect to the line that we just put in there. Now notice, I'm not terribly picky. It doesn't need to be solid. In fact, I'm going to recommend don't even do it super dark. If at the very least you do something like this, that is going to be sufficient. Because let me tell you a quick story. This is the last problem anyways. And let me zoom out here in case anyone on Zoom is still writing down some of those rules. They are posted in Google Classroom also if you need to find them again. But let me tell you a quick story. And this problem would be a good example of it. When I was teaching traditional high school, had a bunch of freshmen, we're going through problems like these, and I warned them. I said, don't shade it in super dark. You're going to get frustrated because mistakes happen. Well, I had a student. It happened to a couple, but I had a student who, for whatever reason, liked the way it looked, liked shading it in, shaded it in super dark, pretty much used half of their pencil to do it. Super dark, all the way to the edge, no blank space, visible. And I walked around and I said, we'll call the student Johnny. I said, Johnny, when you were rewriting it in slope-intercept form, did you divide by a negative? He said, yeah. I said, what does dividing by a negative do? He stared at me and said, it flips the sign. Here's what that meant for poor Johnny. He shaded on the exact wrong side of the line because the sign was supposed to have flipped. So Johnny had to take his eraser and erase and erase. And you all know when you shade super dark on a piece of paper, you're never going to get it all off of there. And then he had to go and shade the opposite side. Don't be like Johnny. His name wasn't Johnny, but don't be like Johnny. Don't shade super dark to where if you make a mistake, it's a pain in the butt to go back and adjust. Because you will make a mistake. That's all part of it. But what do you think? Equations are a little bit faster. They don't have the extra information to check. But with this information in your notes, or for you guys who are writing it down, you've got all the pieces you need. You just need to identify it. And in order to be able to identify all the information you need, what form does it have to be in? Slope-intercept form. Y needs to be by itself. So here's what I'm going to do before I say anything else silly. I'm going to